Thank you. Thank you for your very kind words. It is bad form to begin a lecture with an apology, but I do think that I owe a statement of clarification. I should say right at the outset that I am neither an expert in this field nor have I worked in this field. Indeed, although this lecture has been announced as a colloquium, I should stress that this is really a part of the series of introductory lectures that I've been giving to summer students, where my primary objective has been to be as pedagogical as possible. And it was agreed between me and the students that I would rather not rush through the portions. So my lectures generally exceed the customary 60 minutes. And so will this one. I'm terribly sorry, but then naturally it's only the students who are required to stay on till the bitter end. Others can choose to leave. So let's begin. And the best place to begin is right at the beginning. Our story begins around 1949 with the discovery of a radio source in the constellation Cygnus, the Swan. A bit of history surrounding that discovery. In 1949, John Bolton in Sydney, Australia, decided to do some radio observations with higher angular resolution than had been possible before the war. Please remember that in 1949, the Second World War had just ended. People didn't even have food to eat, and therefore there was no question of money for expensive research equipment. All that John Bolton could get was a few Yagi antennas like we used to have on our terraces for receiving television signals before DTH came to India. But then he did something very clever. John Bolton remembered his physics from his undergraduate days in the Cavendish Laboratory in Cambridge. He remembered the principle of Lloyd's mirror. So what he did was to set up a simple Yagi antenna on at the edge of a cliff just off the Sydney harbour, and he constructed with a single antenna an interferometer by using the Yagi antenna and its mirror reflection on the surface of the sea as the second component of a two-element interferometer. But he did more than that. During the day, the level of the sea goes up and down because of high tide and low tide, and therefore in an 8-hour observation, he was able to do interferometric observations with different separation between the original antenna and the reflection. Exceedingly clever idea. Now this idea was pursued by his colleagues. Yes, with this idea, he made a very revolutionary discovery. Namely, the Crab Nebula, the most celebrated object in the sky, was a powerful emitter of radio radiation. And as we discussed in one of the earlier lectures, that heralded the beginning of relativistic astrophysics as we understand today. But our story today is about Cygnus. Hay, Parsons, and Phillips, using that same cliff-top interferometer, discovered a radio source in the constellation Cygnus. Halfway around the world, in Manchester in England, Hanbury-Brown and two of his students, Jennison and Dasgupta, observed this same source with an improvised interferometer of a different kind, an intensity interferometer. What they did was, they had in Manchester in the physics department a small antenna with which they observed the sky, and then they made an identical antenna, put it on a jeep, and they took it outside Manchester, somewhere outside, and observed. And those days, of course, the only recording medium was a paper chart recorder where the needle goes up and down and records the power that is recorded, the square of the voltage, if you like. Then they came back and then tried to correlate the fluctuation in intensity observed at the two sites. They found fringes, and they went down with that, and they made a very remarkable discovery with which we'll begin our story. But I cannot resist but to pose a very interesting challenge to the students in the audience who are part of my course. What is this intensity interferometer? It's a truly revolutionary idea. First of all, when Hanbury-Brown decided to do this in the radio, nobody bothered. You know, radio engineers, they're crazy. They don't understand physics, let alone quantum mechanics. Let them do what they like. Don't bother me with that. But then Hanbury-Brown, buoyed with the success of his observations in radio, decided he will now do it at visible wavelength. And he went and bought some old searchlight mirrors that they had during the Second World War. And he said, look, what I will do is repeat what I did at visible wavelength and try to measure diameters of very faint stars that Michelson could not measure. Nobody was bothered when Hanbury-Brown did this at radio wavelength, but they were shocked out of their wits. And the cat was among the pigeons when he said, I'm going to do this in the visible, because in the case of faint stars, you're not dealing with waves, you're dealing with photons, you're dealing with single photons arriving one at a time. And it seemed like this idea of Hanbury-Brown was just a blatant violation of Heisenberg's uncertainty principle. Why? Please remember that we are told in first chapter of any quantum mechanics book that even a single photon will produce fringes in a double-slit experiment. We are told rather sternly that you add the two amplitudes and then square it. We are told that if you try to detect the photon going through either of the slit, the interference will go away. This is rule number 1 of quantum mechanics. And please remember, in a Michelson interferometer, we preserve the phase of the two waves, and then we add the amplitudes, and then square them, and then we get the fringes. So what Hanbury-Brown said was, look, I will use simple searchlight mirrors, a whole lot of them. I will collect the signal, I will amplify it using a photomultiplier tube, and then combine and correlate the signals. Now, this was a horrible idea. This outraged the physics community. As Hanbury-Brown has written in his book, they waved around Bibles like Dirac's book on quantum mechanics saying, no, you can't do that. This is a violation of Heisenberg's uncertainty principle. Hundreds of papers were published in leading journals like Physical Review pointing out why this idea will not work. Even Feynman doubted it for a while. Eventually, he put this as problem number 1, chapter number 1 in his theory of fundamental processes. But Hanbury-Brown, being a good experimentalist, couldn't care less about the theoretical high priests. It's best to ignore them. So he went ahead and did this, and of course managed to find the diameters of faint stars. And when the paper appeared in Nature finally in 1957, it was accompanied by another masterly paper by Purcell in Harvard. The first sentence of that paper is still etched in my mind. Purcell said, the intensity interferometer of Hanbury-Brown is not only not a violation of quantum mechanics, but is an illustration of one of its fundamental principles. So I leave it to you, the students of my course, to take this as a challenge. So next Friday when we meet, you should tell me why this is not a violation of quantum mechanics. Nothing further about this. But I should say that what Hanbury-Brown and Jennison and Dasgupta found was this radio source in the constellation Cygnus was actually 2 sources, because now they had angular resolution to see that. Once the position of these 2 sources was known, Walter Baade and Mick, 2 of the most celebrated astronomers of that epoch, identified the elliptical galaxy in the constellation Cygnus right bang in the center of these 2 radio sources. And the discovery of this radio galaxy in the constellation Cygnus created a great buzz, and thus began a new chapter of astrophysics. And with the intensity interferometer, the quest for higher and higher angular resolution also began. Intensity interferometer was not pursued seriously, but what was pursued was the idea of a very large telescope using the rotation of the Earth, and these 2 techniques were pioneered by Sir Martin Ryle at the Cavendish Laboratory, for which he was awarded the Nobel Prize for Physics in 1973. It's a great pity that Hanbury-Brown was not awarded the Nobel Prize, because I still maintain that the paper by Hanbury-Brown on Twiss was the very first paper on quantum optics. You will see how fundamental that idea of intensity interferometry is if you figure this out. So there it is. A few years later, in 1970, Sir Martin Ryle in Cambridge made the first aperture synthesis telescope on a railway track. He had a whole bunch of antennas, 1 mile long, 1.5 kilometers long, and he could move the telescopes at varying positions. So he synthesized a one-dimensional aperture and used the rotation of the Earth also. And then he made this very high-resolution map. And there is the optical galaxy, identified by Bader and Minkowski. And this is the radio source. And what you clearly see is 2 lobes of radio emission, very extended lobes, with 2 hotspots over there. This remarkable observation by Sir Martin Ryle triggered Martin Rees, now Lord Rees. Except for Archbishop of Canterbury, he has been everything in Britain. And his young student, Roger Blandford, I remember I was in the Cavendish at the time. They were working in the Institute of Astronomy across the road from Cavendish. They advanced a very revolutionary idea that the radio lobes in Cygnus was produced by 2 relativistic jets emanating from the central body. So the idea was that these 2 hotspots are created when the ramp pressure of the relativistic jet equals the pressure of the intergalactic medium. Imagine you are in the ocean beneath the surface of water, and you have a high pressure hose like the ones that the firemen use. If I turn the hose on, the water will go in a jet. Finally, at a place where the ramp pressure equals the pressure of the seawater, you'll find a spot there, and then you'll find a backflow. Right? So the idea was that's exactly what is happening. The lobes are created by the backflow, and the hotspots are created where the ramp pressure of the jet equals. Of course, no jet is seen. This was a conjecture. This was a conjecture. And they further went on to say that the jet consists of relativistic electrons and perhaps positrons, and the wind carries with it a frozen-in magnetic field, so it is a plasma that is going out, very much like in the Crab Nebula. We discussed how the Crab pulsar produces a relativistic wind. And they said that the radiation that we see in the lobes is synchrotron radiation, and the enhanced emission at the edges of the radio lobe comes because there is a bow shock created there. Particles are further accelerated at the bow shock, and you have synchrotron emission just like in supernova remnants. This was a conjecture by Rees and Blandford, but no jet was seen. Years later, when the aperture synthesis telescope in New Mexico in America was completed, known as the VLA, the Very Large Array, the jet was very clearly seen. This confirmed the idea that the radio lobes are created by relativistic particles emanating in a jet, and that the 2 hotspots found a natural explanation. And then they found the hotspots in optical emission also. And then came, in the quest for higher and higher angular resolution, very long baseline intercontinental interferometry, where you have radio telescopes all over the world. And we have 2 telescopes, the Wooty telescope and more recently GMRT, were also part of this at various times of the international network. What is the basic idea of intercontinental interferometry? What you do is measure visibilities, Fourier components of brightness, in widely separated telescopes. You observe them simultaneously, and you coherently record the radiation. In other words, you preserve the phase, unlike an intensity interferometer where you throw out the phase. How do you synchronize the observations? Some sort of a global positioning system was used. These days we have GPSs costing 3 or 4 rupees in our cell phones. The first GPS receiver that I saw cost about 5 lakhs, and it occupied a whole rack in the laboratory. The point is that a global positioning system allows you to align the time at these various radio telescopes to a narrow window of something like tens of nanoseconds, if you're lucky. Then what you do is, every station has a hydrogen maser, which is your atomic clock, if you like, which gives you the frequency standard. And please remember, at different parts of the Earth, the atmosphere is boiling at a different rate. There is no correlation between the atmospheric fluctuations. Therefore, the time that is available for coherent observations is rather limited because of atmospheric fluctuations. And as we will see, this problem gets more and more severe as you go to higher and higher frequencies. After the observation, you bring all these magnetic tapes by plane to a central location, and then you align them in time, and then they're cross-correlated, and you do standard interferometry. So here are the results of such intercontinental baseline interferometry. There is our Cygnus radio lobes, and you see how the central region is expanded further and further by going from 6 centimeters to 7 millimeters using intercontinental baseline interferometry. Here is the giant galaxy Centaurus A. That is the central region of Centaurus A invisible. That is the galaxy in infrared. And then in radio, you see the spectacular radio lobes. And then in X-ray and in radio, you see these jets, and the jets in X-ray and radio are perfectly aligned with respect to one another. Here is a quasar galaxy NGC 383, and the central region seen with intercontinental interferometry. Here is another quasar 3C273, and the central region expanded and seen to the right in intercontinental interferometry. Now, one of the remarkable things about these radio galaxies is that in many of them you see only one jet. For example, in M87, we'll come to this towards the end of the talk, even though you clearly see radio lobes in both directions, you see only one jet, and that jet is seen over the entire electromagnetic spectrum. Visible, X-rays, radios, gamma rays now. The jets are all aligned at all these wavelengths. But you see only one jet. Here is another example, 2 examples. 3C175 and some other galaxy, you see only one jet, but clearly you see 2 side lobes. Here is the granddaddy of them all, NGC 6251, seen at higher and higher angular resolution. This is just 3 light years in size here, and here is 1 million light years, 3 million light years. So here is a perfectly aligned jet, one-sided jet, which is 3 million kilometers long, 1 million parsecs in size. Now there is consensus that although you see only one jet, jets emanate from the central object, which we will soon identify as a supermassive black hole, in both directions. One of the ideas that was explored for a few years, that for some reason, the central object, the jet from the central object does a flip-flop. Sometimes it points in this direction, sometimes it points in this way. So a balloon is inflated whenever it is pointing in that direction. Why such a jet should flip? Nobody had any clever ideas, so that idea soon fell out of favor. And the idea that was suggested by Blanford and Rees in their original publication is that a more plausible reason is that there is a Doppler boosting of the intensity in the jets that's coming towards you compared to the brightness of the jet that's going away from you. If this Doppler boosting is the correct explanation for why you see only jet in one direction, then the jet has to be very relativistic. Why? So what is Doppler boosting? Let us recall the basic formula from Lorentz transformation, 2 frames moving with respect to one another with a uniform velocity v, and we know the rate of ticking of the clock in the 2 frames are given by this simple expression. But if that frame is moving at a certain angle theta with respect to you, then this formula is slightly modified in the numerator, I pick up a factor which is 1 minus v cosine theta, where theta is the angle that blob makes with respect to the line of sight. Well, you know that in this situation, since the rate of ticking of the two clocks are different, therefore the frequencies will be different. And this is, of course, the famous formula for the Doppler shift, relating the frequency emitted on the right-hand side to the frequency observed on the left-hand side. The denominator, of course, is the traditional Doppler shift formula. When the source is moving with a velocity v, which is very small compared to the speed of light, v squared by c squared can be neglected. Therefore, the numerator just becomes unity, and we recover the non-relativistic Doppler formula. But this is the proper formula for Doppler shift in special relativity. Therefore, we already know that because the blob is moving, the frequency it emits is different from the frequency that we observe. But what we want to know is there going to be any difference also in the intensity it emits and the intensity that you measure. Remember, we are trying to understand one-sided jets. Well now, so let's be very clear about what we mean by intensity. So let me therefore define it very properly. I have an area dA through which radiation is passing, and normal to that is this unit vector n. Around that there is a solid angle d omega. Now I defined what is known as the specific intensity I knew. It is the energy crossing an unit area per unit time in a frequency interval d nu and going into a solid angle d omega about n, which is normal to the surface. So these dimensions are very important. Dimensions are extremely important. Okay? So, once again, the specific intensity differs from our notion of intensity because of the way I have defined it. The specific intensity defined that way has a very remarkable property that it is a constant along the ray. The usual intensity decreases as 1 over r squared, as Newton taught us a long time ago. But the specific intensity is constant along the ray. This is what astronomers refer to as brightness. Brightness is independent of distance because you are referring brightness to the energy going into a solid angle. That's all that I care. The solid angle that it subtends, I don't care how far or near it is. Okay. Another very interesting property is that I nu over nu cubed is a Lorentz invariant. So I leave it as a simple exercise for you to verify this statement. Namely, the specific intensity divided by nu cubed is a Lorentz invariant. Specific intensity is by itself is not a Lorentz invariant. Therefore, if I have a source emitting a specific intensity I prime at a frequency nu prime, then it is related to I nu at the frequency nu that we measure by the relation that I nu over nu cubed is a Lorentz invariant. And therefore, the specific intensity that we measure, the observer measures, is related to the specific intensity of the source by this factor dq, which is, of course, the Doppler factor given over there. The important thing to appreciate is that if the jet is even mildly relativistic, namely V over C is 0.97, and gamma is a very modest 4, then this Doppler factor can be 10 or more, and therefore d cubed can be 1000 or more. Therefore, if I have two jets, symmetric jets, one coming towards us, making an angle theta, of course, and one going away from us, then the ratio of the surface brightness of this jet to that jet will be given by 1 plus beta cos theta divided by 1 minus beta cos theta to the power n, where n is of the order of 2.5 or 3. It is 2 plus alpha, where alpha is the index of some synchrotron radiation, 0.75 or thereabouts. Okay, so roughly it's about 3. Therefore, you see very clearly here that the surface brightness of the jet that's coming in your direction or making an angle theta will be boosted in specific intensity compared to the other jet. And Martin Rees and Roger Blandford's point was that is the reason why you see one jet and not the other jet. The jet has to be relativistic. But if the jet is relativistic, they pointed out in their very first paper one other thing. They said you will observe superluminal motion. You will observe apparent motion at speeds greater than the speed of light. What is the superluminal motion? Let's go back to our original diagram. Imagine there is a black hole or some source at the point A, and it is ejecting a blob which is moving with a velocity v in the direction theta with respect to the observer. And in a time delta t as measured by the clock on the blob, it moves a distance v delta t and arrives at a point B. So what we are interested in is what is the time of arrival of the signal from A and what is the time of arrival of the signal from B. Please remember that by the time the source has arrived at the point B, the source is closer to us. Therefore, that's what gives rise to Doppler shift. Therefore, the apparent velocity we see, the apparent velocity in the sky is v delta t sine theta divided by t2 minus t1, which is the arrival time of the pulses at from A and from B. And this apparent velocity can be divided with c, and we write a neat expression that beta apparent is beta sine theta divided by 1 minus beta cos theta, where beta, of course, is just v over c. So please derive this as very simple algebra. I expect you to fill in the details, okay? So let's look at that once again. The apparent velocity is related to the true velocity beta by that formula, and for a fixed value of beta, that expression has a maximum when cos theta is equal to beta. And therefore, the maximum value of the apparent velocity is not beta, but gamma times beta. Where gamma is 1 over square root of 1 minus v squared by c squared, it can be a very large number for a relativistic jet. So let's plot this apparent maximum velocity. What is plotted on the y-axis is the apparent transverse velocity in the plane of the sky as a function of the angle the blob makes with respect to the line of sight for various values of beta, beta being the actual velocity with which the jet is moving or the blobs are moving. So you see, for example, if the beta is 0.998, then the apparent velocity of expansion can be as large as 15 times the speed of light. This is no contradiction of special relativity. It is because of special relativity, not in spite of special relativity. Many years later, here is the quasar 3C273, the very first quasar that was ever discovered. And you see there's a cover picture from Nature of the superluminal motion. And here you see the superluminal motion in the galaxy M87, which we will come to towards the end of this talk. Very clearly from the epoch 1994 to 1998, you see an apparent distance of 24 light years traverse on the plane of the sky, which is superluminal expansion. Here is the quasar 3C273, yet another example of superluminal motion. Therefore, both the Doppler boosting of one side of the jet as well as the observed superluminal motion in the very long baseline interferometric observations confirm the original conjecture of Blanford and Rees that these two blobs and the hotspots are indeed energized by relativistic jets consisting of electrons and positrons. Please remember, there may be jets, jet may consist of protons also, but they do not radiate. Remember our discussion of synchrotron radiation? The mass enters in the denominator as m squared in the intensity of radiation. Therefore, the radiation from protons is 1,000,000 times less than the radiation from electrons. Now let's turn to a more important discussion, namely the energy content of these lobes. It's mind-boggling, absolutely mind-boggling. The energy content in each of these lobes is an unbelievable 10 to the power 61 ergs. The sun radiates 10 to the power 33 ergs per second. There are 10 to the power 7 seconds in a year, and our universe is 10 billion years old. So this is more energy than the sun would radiate in the entire history of the universe. The central engine, whatever it is, has a luminosity of 10 to the power 46 to 10 to the power 47 ergs per second. The luminosity of the sun is 10 to the power 33 ergs per second. So we are talking of a central source whose luminosity is mind-boggling. Please remember, even at that rate, in order to pump that much energy into the lobe, the jet must have been pointing in that direction for 10 to the power 8 years. The jet could not have precessed. This is a very challenging problem for black hole physics because you could, in principle, have free precession of the black hole, so you would expect the jet to precess. It cannot precess because it's pointing in that direction for 10 to the power 8 years. And please remember, the jet is awfully long, 3 million light years in the case of 6251. Therefore, two questions arise. One is what confines and collimates the jets over incredible distances of millions of light years. And secondly, for the jet to remain relativistic, there has to be in situ continuous acceleration. Because please remember, as the electrons radiate, they lose energy in a time scale which is dE by dt divided by E divided by dE by dt. Remember, the amount of money that is left in your bank depends on how often you go to the ATM and how large is the amount you withdraw from it. So electrons lose energy. Therefore, if they are still radiating after 3 million light years, there has to be in situ acceleration. These problems, whereas there have been conjectures, are still not fully solved. Now let's turn to the central engine, because that's our story. As I said, the central engine is measured to have a luminosity of 10 to the 47 to 10 to the 46 to 10 to the 47 ergs. And the central engine is generally a quasar. It could be a radio loud quasar, it could be a radio quiet quasar. But the important thing is that that object is always at the center of an elliptical galaxy. It is never at the center of a spiral galaxy like our galaxy or the Andromeda galaxy. Why this is so is a different story. As I said, the luminosity is more than 10 to the power 10 times the luminosity of massive stars, the kind of stars that produce neutron stars and black holes. Now, here is the punchline. A luminosity of 10 to the power 46 ergs per second implies that the mass of the central engine must be more than 10 to the power 9 solar masses. Why is that? We can understand that by going back to something that we learned from Eddington way back in 1923, which we have already discussed, but let me repeat the argument. Let's consider a gaseous star. And at some imaginary distance from the center, let us construct a unit volume which has n protons and n electrons for simplicity. Let's assume that the pressure of gas is unimportant and it's mainly the radiation pressure that is supporting the star. In other words, this unit volume over there is in radiative equilibrium. In other words, the radiation force acting on it is precisely equal to the gravitational force acting inwards on it. What is the radiative force of the unit volume? It is L divided by 4 pi r squared C multiplied by the cross-sectional area of the unit volume, which is number of electrons multiplied by the cross-section of each electron, which is the Thomson scattering cross-section. And what is the Thomson scattering cross-section? It is 8 pi by 3 square of the classical electron radius. And what is the classical electron radius? It is when the electrostatic energy is equal to the rest mass energy. And what is the gravitational force acting on the unit volume due to the mass interior to that? That is Gm, capital M, multiplied by the mass of the unit volume divided by r squared. I've ignored the mass of the electrons in comparison with the mass of the proton. And therefore, for radiative equilibrium, the gravitational force acting on the unit volume, which is the left-hand side, must be equal to the radiative force acting on the unit volume, which is the right-hand side. I can now solve this for the luminosity, and I get one of the most beautiful and magical formulae in all of physics that I know. It says the luminosity of the star can never exceed a value which is given uniquely by the mass of the star apart from fundamental constants. There's no adjustable parameter in that. You tell me the mass of the object, and I will tell you the maximum luminosity it can have. The maximum luminosity it can have is 10 to the power 38 ergs per second, with the mass being measured in units of mass of the sun. And the argument is, if the luminosity of the object exceeds this value, then radiation pressure will blow apart the star. So this is a limiting luminosity. Therefore, a luminosity of 10 to the power 47 ergs per second implies that no matter what the mechanism is, we don't know what the mechanism is, that object must have a mass of at least 1 billion times the mass of the sun. Much more, maybe 10 to the power 10, 10 to the power 11, but at least 10 to the power 9. So this is an incredibly powerful argument. And this was realized, I remember as a student, when people spoke about this, there was just a whisper in the room. I said, my God, 1 billion solar mass? And then I remember the day when Roger Hayrock from University of Michigan came to Chicago to give a colloquium, where he announced spectacularly that this quasar, the flux is variable over a year. This shocked the wits out of everybody. A radio source changing in luminosity in a year, because this immediately told them that the object cannot be, if the variability timescale is delta t, then the object has to be of a size less than c delta t. Please remember, we have discussed this argument before. This was the argument that led Jocelyn Bell to conclude that that pulsar must be a neutron star, because the fluctuation timescale was so short that the object had to be the size of a football field or something like that. So, then there was an argument about it. Can we really be sure that the central object is a black hole? Then optical astronomers showed that the variability is not in the time scale of years, but is in the time scale of days. That is bad news. And then came the X-ray and gamma ray astronomers and found variability in the time scale of minutes. This was the last nail in the coffin. So it became absolutely clear, and it became clearer by the year, that quasars, as well as all other types of active galactic nuclei, are powered by supermassive black holes. You couldn't generate that much luminosity without that much mass, and the variability implied a distance which is small compared to the Schwarzschild radius. Now, with the advent of the Chandra X-ray observatory, it has now emerged that all galaxies harbor massive black holes. There may be millions of solar mass or billions of solar mass, but they all have them. 30 years ago, this was not at all clear. Nobody suspected galaxies like ours as a black hole in it. But today we know. Why there are no active quasars in every galaxy, including our center of our galaxy? Well, that is to be understood, as Martin Rees had said already way back in 1974 or 75, that it should be understood in terms of whether the black hole is being fed or not. So, for example, unless sufficient matter accretes onto the black hole, it will not emit enough radiation. Please remember, unlike a neutron star, a black hole doesn't have a hard surface. Therefore, the efficiency of converting gravitational potential energy to radiation is rather low. So it must accrete quite a bit of matter. Therefore, the 3 billion solar mass black hole in the center of a galaxy is suffering from malnutrition. That's why it is not a quasar. All right. Now, stars in close orbits near the black hole can be tidally disrupted, and then the gas falls in, and in the process emits radiation, usually comes out as X-rays. Gas clouds can also fall in. But in every case, because you're talking a matter from an orbiting companion, the matter has angular momentum, and therefore it has to first form an accretion disk. And then matter has to drift inwards in the accretion disk due to some sort of a friction. Otherwise, the orbits will be Keplerian, and you will not have matter falling into the black hole. Please remember that the gravitational potential energy is released in the process, and that's what we see as radiation. Now, a luminous quasar radiating 10 to the power 46 ergs per second must accrete almost 1 solar mass of material per year. This is an enormous amount of material, because please remember we discussed the concept of Eddington accretion rate. And therefore, even at the maximum possible accretion rate, it will take an awful lot of matter to fall in before effectively 1 solar mass of material falls in a year. Now, detailed studies done by various people in the last 25 years or so have taught us the following thing. Whereas the accretion disk at the large distance from the central object may be very thin and supported essentially by rotation, but in the inner regions, radiation pressure puffs up the disk rather dramatically. Because gas is getting hotter and hotter as you come in, because the gravitational potential well is getting steeper and steeper, and therefore radiation pressure is more dominant, and therefore what you really have is a funnel near and around the black hole, and this funnel, it emerged during the last 20 years or so, plays an essential role in forming and collimating what becomes the jet, which then goes for millions of light years. How is the jet produced? Well, the most significant mechanism was advanced by Roger Blanford, who, for the students in the room, who is now very closely connected with this institute, at that time he was a student, and he advanced an idea which was sort of borrowed from how pulsars work, neutron stars work. So the idea is you somehow use the magnetic field which is threading the accretion disk material and the associated electric field generated by the magnetic field and use this as sort of a dynamo. Please remember, a neutron star is endowed with a large magnetic field and an associated electric field, V cross B. But a black hole does not have a magnetic field. So you're talking the magnetic field that is threading the accretion disk and electric field produced by hydrodynamics. So the details are very subtle and very complicated, but this is the only sort of mechanism that we still have, sort of as a generic mechanism for how jets are accelerated. I'm not trying to explain to you. Now, active galactic nuclei come in all sorts of names. Seyfert galaxies, Seyfert 1, not to be confused with Seyfert 2s, BL-lac objects, quasars, radio loud quasars, radio quiet quasars. For about 20 years, they were all treated as different objects. But now there is a unified picture. There is a central black hole which is surrounded by an accretion disk. And surrounding the accretion disk at a much larger radius, there is a thick torus of molecular gas and molecular clouds. Depending on your viewing geometry, whether you're looking straight down the jet, then you call it a BL-lac object. If you look at it from an angle, you call it a Seyfert 1 object or a quasar. So there is now a unified picture, which has been now generally accepted, that all active galactic nuclei are like the picture shown on the left. There is a central black hole with an accretion disk which is puffed up near the center, not shown in that cartoon. But depending on the viewing geometry, you see it as different objects. Yes, yes. Always at the center of an elliptical galaxy. At the moment, yes. They're also not very massive black holes. There are millions of black holes. So we'll come to that at the very end. Perhaps by the time they grow, they also become elliptical galaxies. That is the sort of picture. So the elliptical galaxies in the scenario would be the end point of the evolution of spiral galaxies through mergers and collisions. So right towards the end, I will say a few words. So what's the evidence we have for supermassive black hole? I think the first convincing circumstantial evidence came from the galaxy NGC 4258, which is this galaxy. And what they saw was an accretion disk in which there were a lot of water vapor masers, some of them moving away from us, some of them coming towards us, and some going in transit at perpendicular direction. This is the radial velocity, and the curve is Keplerian, 1 over square root of r. So what you see, first of all, these masers, water vapor masers, are at a frequency of 22 gigahertz. Because they are masers, the lines are extremely sharp in frequency. Therefore, you can measure the velocities with incredible accuracy. For example, in these cases, the velocities of these jets, the velocity in the accretion disk can be measured to an accuracy of less than 1 kilometers per second. Absolutely mind-boggling. The inner edge of the observed accretion disk, the velocity is still very modest. It's only 1,000 kilometers per second. It's still only 1 over 300th of the velocity of light. So it's not really relativistic motion in that sense. The motion is perfectly Keplerian. From that you conclude that the central object in this galaxy is of 3.6 times 10 to the 7 solar mass. And given that mass is constrained, circumscribed within a certain distance, people concluded that it is either almost certainly a black hole, or given enough time, it will become unstable and collapse to a black hole. So it's a circumstantial evidence. The most spectacular circumstantial evidence comes from the center of our galaxy in what I consider is one of the most beautiful observations in all of astronomy in recent decades. The observations of the motion of stars at the center of our galaxy, which is 30,000 light years away. Most of the stars that we see in the sky, even with the Hubble telescope, are in our backyard, just hundreds of light years away. Here we are talking of 30,000 light years away. So you have to observe in the infrared, and you have to use very fancy adaptive optics techniques. And people have developed these techniques. And these are the actual tracks of the stars. You see not only velocities, you see acceleration. And from these observations, people have concluded that there is a black hole at the center of our own Milky Way galaxy. It's 3 million solar mass mass. But to be fair, all this evidence is circumstantial. It's not real proof that it is black hole. And so we come to the observations that was in every newspaper 2 months ago. The potential imaging of a black hole at the center of the giant elliptical galaxy M87. There is the elliptical galaxy M87. It's at the center of the Virgo supercluster, to which our own cluster of galaxies belongs, to the supercluster. This is right there at the center. It is the granddaddy of all elliptical galaxies. And 100 years ago, the astronomer by name Curtis noticed that there is a linear feature which pointed right to the center of the galaxy. He actually made a point of mentioning this. Today, with the advent of interferometry, particularly very long baseline interferometry, we know that the linear feature is a jet. It is a relativistic jet of plasma blobs with a large Lorentz factor. We see it over the entire electromagnetic spectrum up to gamma rays. What you see here is a jet in radio, X-rays, optical, and more recently in gamma rays. And let me remind you, it is a one-sided jet. Some years ago, this jet was imaged at 43 gigahertz, which is a very, very high frequency. using intercontinental baseline interferometry, and you see the central region seen at higher angular resolution, seen at an even higher angular resolution, and there at the bottom is 0.01 parsec. 1 parsec is 3 light years. So you're really looking down at the black hole sort of dimensions, right over there. And this is the general picture. But that wasn't good enough. Wasn't it good enough? At 43 gigahertz, VLBI achieved an angular resolution of 3 times 10 to the power minus 4 arc second. Now we know that there is a giant black hole at the center of M87, and dynamical considerations and luminosity consideration had given people an estimate of the mass of the black hole, that it must be about 6 times 10 to the power 9 solar mass. And we know what the Schwarzschild radius of a black hole of that mass ought to be. So if I put a black hole of that size at that distance to M87, it will subtend an angular size of about 4 to 7 times 10 to the power minus 6 arc seconds. That uncertainty 4 to 7 comes from the uncertainty in the estimate of the mass of the black hole, depending on who you believe. So you see, we were able to achieve an angular resolution which was still short by a factor of 100 compared to what you need to actually image the central black hole in M87. Then, of course, people said, go from 43 gigahertz to millimeter waves, to 200 and odd gigahertz. So VLBI was attempted 2012 to 2015 at 1.3 millimeters. Now that was really considered science fiction 20 years ago. Why was it considered science fiction 20 years ago? Because the principles are the same. Only have gone to higher frequencies. But precisely because they have gone to higher frequencies, there are incredible technical challenges. For example, as you go to higher and higher frequencies, the noise in your receiver increases. Therefore, you have to have quantum receivers at cryogenic temperatures. Secondly, higher the frequency, more is the absorption due to molecules in our atmosphere. Please remember, our atmosphere has heavy molecules, such as water molecule. These have vibrational and rotational energy levels, which are at millimeter wavelength, and therefore, as you go to higher and higher frequency, the opacity of the atmosphere increases. This is why millimeter wave telescopes are on top of Andes Mountain and places like that, because you try to go as high as possible. And then, as you go to higher frequencies, atmospheric fluctuations become more violent, and they also become more uncorrelated between different places. Therefore, the time that is available for you for coherent observation, which can eventually be added, becomes shorter and shorter as you grow to higher and higher frequencies because of atmospheric turbulence. Secondly, to observe at millimeter wavelength, you need a dish, an antenna of very high surface accuracy. GMRT has 45-meter antennas. It's made of chicken mesh because you're dealing with a meter wave. But to reflect a millimeter wave, you need a surface, hard surface of very high surface accuracy. Those antennas are very difficult to make and extremely expensive. And the angular resolution depends on lambda by d, where d is the diameter of the dish. So as you go to millimeter wavelength, your angular resolution is crashing, even though the lambda in the numerator is decreasing. But these are the kind of challenges. So in 2015, VLBI was done at 1.3 millimeters, and M87 was observed at 1.3 millimeters. And they achieved an angular resolution of 20 micro-arc second. Previously, it was 4 times 10 to the power minus 4 arc seconds at 43 gigahertz. They achieved 20 micro-arc second. What is 20 micro-arc second? It so happens to be the angular size the black hole at M87 will subtend. So the angular resolution achieved in 2015 was sufficient to resolve the shadow of the black hole in M87. But it didn't. what they found was an emission, a ring-like emission whose size was 40 microarc second, the resolution was 20 microarc second, but the central depression of the intensity, which we now identify as the shadow of the black hole, was not seen. And why was it not seen? It was understood as due to poor baseline coverage, as antenna engineers would say. Please remember, each baseline of pairs of antennas measures one particular Fourier component of the visibility. So they didn't have enough frequency or Fourier components or enough sampling in real space to actually form a central image. And that's what led to the concept of the Event Horizon Telescope, which was just yet another intercontinental baseline interferometric network. But except the location of these networks, antennas in the network was very carefully chosen to provide them with the kind of Fourier components that they couldn't afford to sacrifice in these observations. And also many spectacular improvements were made. And to me, it's a matter of some sadness that when newspapers are flashing all these pictures of black holes in their front pages, very little credit was given to the technological achievement, the engineering achievement in making VLBI at that frequency possible. What did they achieve? For example, this observation, they use Josephson junctions, superconductor, insulator, superconducting junctions to detect the millimeter wave radiation, to beat the noise, to have actually a quantum detector. Secondly, the noise temperature by using a Josephson junction was decreased by more than an order of magnitude, which was tremendous technical achievement. The bandwidth was increased by a factor of 30. Where does the bandwidth come from? Please remember, every engineer will tell you the signal to noise ratio will be proportional to 1 over square root of the bandwidth, and the observing time, that is just from random walk, square root of time comes. So you need to increase the time of observation, you also need to increase the bandwidth. So they managed to increase the bandwidth by a factor of 30. Now then the signal is mixed in the SIS junction with a very stable local oscillator, then converted to a lower frequency, and then standard technology takes over. There is no big problem once that is done. And it is these plus various other improvements that were central to the observations that they carried out in April 2017, which was then published in April 2019. Now, before the observations, what do we expect the environment to be near the black hole? As I already said, the matter captured by the gravity of the black hole will form an accretion disk. And this angular momentum of the disk may or may not coincide with the angular momentum vector of the black hole. It may even be anti-parallel, or it may not be oriented, in which case there will be a precession of the black hole enslaved by the disk. Now, matter, as I said, flows in towards the black hole because there is some sort of a viscosity, some sort of a friction. What is the origin of this microscopic viscosity is still not very clear. It was first suggested by people in Zeldovich's group in Moscow, and that's where matters stand now. Everybody believes that there is an alpha parameter, a microscopic viscosity, which is responsible for the radial motion. Please remember, I leave it to you to work it out, the students in the audience, that for matter to go in, some angular momentum has to be extracted. Therefore, from the outer regions of the disk, matter should also go out. Otherwise, you will not conserve angular momentum. Work it out, please, for a simple Keplerian disk. Okay. Now, the temperature of the disk will be several millions of degrees. And a gas at several millions of degrees will primarily emit X-rays. What is the mechanism of emission of X-rays? It is Bremsstrahlung, collision of electrons with the nuclei. The spectrum of this radiation will be given by the thermal velocity distribution of the electrons. It's not black body radiation, it is optically thin radiation. Now, Chandra Observatory has detected many hundreds of such black holes with accretion disks emitting X-rays. Many cases they refer to stellar mass black holes, some cases to intermediate mass black holes, but at the centers of galaxies, it refers to these supermassive black holes. I already said that very close to the black hole, the accretion disk will be very puffed up due to radiation pressure, as shown in this picture. Now, look at the very central region, very close to the event horizon of the black hole, the Schwarzschild radius of the black hole. The conventional wisdom is that in the innermost region of the disk, or the material, is collisionless. There isn't much collision. Therefore, there isn't any Bremsstrahlung. Then what is the radiation radio astronomers observe at millimeter wavelength, if it is not Bremsstrahlung? First of all, if there is Bremsstrahlung, it will be in X-rays. You have no business to be observing at millimeter wavelength. A gas is at a temperature of 10 million or 100 million degrees, will not emit millimeter wave radiation. It will emit primarily X-rays. So what the authors claim is that the radiation that they see at 1.3 millimeters is actually synchrotron radiation due to relativistic electrons gyrating in the magnetic field in the disk. Why do they say so? The spectrum of this radiation, intensity versus frequency, as a signature synchrotron spectrum, and it is also polarized. Remember our discussion of the Crab Nebula, characteristic of a relativistic particle gyrating is that it will radiate predominantly in the plane of the orbit because the emission is beamed in the forward direction in a narrow cone whose opening angle is 1 over gamma. And that radiation will be linearly polarized in the plane of the orbit. If I look away from the orbit, I won't see anything. I have to look in the plane of the orbit. For non-relativistic electron, it's dipole radiation. It will radiate all over the place, but not a relativistic electron. These are the two considerations that led these 150 authors or so of these 5 publications to conclude this must be synchrotron radiation. So the consensus that emerged for the last 20 or 25 years of modeling a black hole with accretion disk is that right near the black hole there is a thick torus of material, collisionless material, it is geometrically thick but optically thin. In other words, it's transparent material, but it is geometrically very thick. It surrounds the black hole. This torus of material is also rotating about an axis which may or may not coincide with the spin axis of the black hole. Now, near the event horizon, the velocity of rotation of this torus will be obviously relativistic, and therefore you expect to see Doppler boosting and various special, not only general relativistic effect, but also special relativistic effect. So what does one expect to see? Well, this is what we expect to see if you are dealing with a Schwarzschild black hole or a non-rotating black hole. What is shown here is a black hole whose radius is the Schwarzschild radius, 2gm by c squared. And what is shown by various curves are the trajectories of photons. If the photon has a very large impact parameter, then it will either escape to infinity in that direction, or it may make a grazing scattering around the black hole and go back to infinity in the direction it came from. There is a critical value of the impact parameter. And general relativity tells you that critical value of the impact parameter is 3 root 3 by 2 times the Schwarzschild radius, square root of 27. So all photons whose impact parameter at infinity is equal to or less than this critical impact parameter will eventually go around the black hole and either escape to infinity or fall in, or if they're even smaller impact parameter, they'll go straight into the black hole. So the last unstable circular orbit around the Schwarzschild black hole, the last knife-edge orbit, by knife-edge orbit I mean the photon will go around a few times, it'll either fall in or escape to infinity, is at a radius of 1.5 times the Schwarzschild radius. So let me show you the same picture in a different way. So what you will see from infinity is a shadow of the black hole. The radius of the shadow will correspond to the critical impact parameter, 3√3/2 times the Schwarzschild radius. And then surrounding the black hole at a radius of 1.5 times the Schwarzschild radius, there is a cloud of photons, the last photons which are orbiting the black hole, which will be there forever and ever, slowly leaking, either falling in or coming out. So when a star collapses, this is where you lose contact with it finally at 1.5 times the Schwarzschild radius, and you will see a reddened glow there, photon cloud. So what you expect to see, ideally, is there is a black hole, there is a shadow cast by the black hole, and then, in principle, there is a cloud of photons. Some of it may come out, and in the process of coming out, they will be subject to all kinds of gravitational lensing effect due to general relativity. So, if it is a curved black hole or a rotating black hole, the picture is a little more exotic. Here, suppose I drop a photon or a stone radially with zero angular momentum. As the stone or the photon approaches the black hole, it will sense the rotation of the space-time because inertial frames are also being dragged due to lens steering effect, and therefore the photon will acquire angular motion. And here is a beautiful example of an angular motion without angular momentum. Angular momentum that you gave it at infinity. You didn't give it any angular momentum, you threw it in radially. So that's a very beautiful example. So the behavior of photons in a curved black hole is more complicated than a Schwarzschild black hole. It has to be evaluated using computer modeling. What do you expect to see? Of course, people have studied this at great length, the whole lot of people. In particular, Falke and his collaborators in the year 2000, 19 years before the observations that were reported in the papers 2 months ago, predicted the following. They said, for accreting black holes embedded in a geometrically thick but optically thin emission region, the combination of an event horizon and light bending leads to the appearance of a dark shadow, together with a bright emission ring that should be detectable through very long baseline interferometry. Its shape can appear as a crescent because of fast rotation and special relativistic beaming. In other words, they suggested you'll see something like this, if you're lucky. And that's what was seen 19 years later. So what is it that you're seeing? This is very complicated to answer, because you have so many parameters that come into this thing. You have a black hole which may be rotating, maybe not rotating. You don't know its angular momentum. You don't know the direction about which it is rotating. You don't know the details of the matter. The hydrodynamics has to be done general relativistically, so you have to do general relativistic magneto-hydrodynamic modeling of the inflow of matter in the accretion disk. You don't know anything about the electron energy distribution. You don't know anything about the magnetic field in the accretion disk. You don't know what is the associated electric field. You just don't know 50 or 60 parameters. So that's why it took them 2 years. So they have done a wonderful job, in my opinion, of varying every conceivable parameter, but in a very systematic and controlled manner, and say, let us see which combination of these parameters will agree closest with what you actually observe. And therefore, they make this suggestion, which you can accept or need not accept in its entirety. For example, in one of the general relativistic magneto-hydrodynamic models, they predict this is what you should see from a torus which is geometrically thick but optically thin, and if the central black hole is a rotating black hole. But you can't compare apples and oranges, because the angular resolution of the theoretical model is practically infinite, whereas the observation is constrained by an angular resolution of 20 micro-arc second. So what you have to do is to take this model and convolve it with a Gaussian beam, which has the same angular resolution as your observation, which is 20 micro-arc second. So there you see the comparison. Therefore, for example, this particular model, which corresponds to that central picture, could be what you're seeing. But perhaps there could be other combination of these parameters. Just to give you an idea of the kind of how the parameters can change, how it look like, let us just vary one particular parameter. Let us consider a black hole spinning about that axis pointing to the left, spinning in a clockwise direction, and let us say the torus is also rotating about the same axis, also in a clockwise direction. Then you will see this. But in this case, you will see that. In this case, you will see this. In this case, you will see that. So they conclude from this that if it is a curved black hole, then the angular momentum of the black hole must be aligned with respect to the jet axis in that particular way, and so on. So here is my cartoon. Please pardon my crude attempt here. I'm trying to describe in a picture, because I believe one picture is worth 10,000 words. You have heard me say this often enough. So there is the black hole. It is spinning about its axis, which is the red arrow over there. There is the jet that is approaching us, the jet we see. And the receding jet is going in that direction, which we don't see. And where are we viewing it from? That is our line of sight. And what is the angle the line of sight makes with the approaching jet? The best fit model suggests that angle is 17 degrees. And as for the torus, they suggest that the torus is rotating also in a clockwise direction. And comparison with simulation suggests that the torus is rotating clockwise around the spin axis of the black hole. And that is why you see that symmetric ring becoming a crescent because of Doppler boosting of the direction that's coming towards us. So what's the summary of the conclusions? They suggest that the shadow is caused by a curved black hole, with the spin pointing in the direction of the jet that we do not see. They have bounds on the spin of the black hole. They conclude that our line of sight is most likely inclined to the axis of the jet by 17 degrees. The observed millimeter wave radiation, they suggest, is synchrotron radiation, which emanates from within few Schwarzschild radii and therefore subject to extreme gravitational lensing. The plasma is rotating in a clockwise direction, and they get a very good estimate of the mass of the black hole, which agrees excellently well with the earlier estimates of 6 times 10 to the power 9 solar mass. So, my friends, has general relativity finally been verified to a satisfactory extent? Not yet. I will be shocked by this statement. Therefore, I'm going to appeal to higher authorities to convince you that this imaging has not settled the question as to whether general relativity has been verified or not. So I must be very precise in what I mean by verification of general relativity. So in 1979, in a talk given at the Einstein Centennial, Dirac said, "I have enumerated the success of Einstein's theory of gravitation. It is a long list, quite impressive. In every sense, the Einstein theory is confirmed." Now, in a lecture given in honor of Telegdi's 60th birthday or 65th birthday, Chandrasekhar profoundly disagreed with Dirac. He said, "It does not seem to me that the success of Einstein's theory are either long or impressive. It is true that his prediction of the different rates of clocks in locations of differing gravity, his prediction of the deflection of light when traversing a gravitational field and the resulting time delay, remember the Shapiro delay? His prediction regarding the precession of the perihelion of Mercury, and finally the slowing down of the binary star in an eccentric orbit by virtue of the emission of gravitational radiation have been confirmed quantitatively He's not quarreling with that. But all these relate to departures from Newtonian theory by a few parts in a million and of no more than 3 or 4 parameters in the post-Newtonian expansion of Einstein's field equations. And so far, no predictions of the general relativity in the limit of strong gravitational field have received any confirmation, nor are they likely in the foreseeable future. This was said almost 40 years ago, 35 years ago. Chandrasekhar says, should one not argue that a theory which generalizes a theory as well confirmed as Newton's theory of gravity should refer to the predictions which relate to the major aspects of the theory than to small first-order departures from the theory it replaces? Would the status of Dirac's theory of the electron, for example, be what it is today if its only success consisted of accounting for Parsons' measurement of the fine structure of ionized helium? The real confirmation of Dirac's theory was provided by the exact departures provided by the Klein-Nishina formula, replacing Thomson's formula for electron scattering, and more particularly in the confirmation of the predictions of the theory relating to the creation of electron-positron pairs and of antimatter. Or would one's faith in Maxwell's equations of electromagnetic field be as universal as it is without Hertz's experiment on the existence and propagation of electromagnetic waves with the velocity of light, and without Poincaré's proof of their invariance to Lorentz transformations? In the same way, a real confirmation of the general theory of relativity will be forthcoming only if a prediction characteristic of the theory and only of the theory is confirmed. The occurrence of black holes in nature as one of the final equilibrium states of massive stars and the natural course of the evolution is not a confirmation of the prediction of general relativity in any real sense. The notion that light cannot escape from a sufficiently strong gravitational field is an obvious inference, not based on any exact prediction of the theory. It depends only on the verified fact that light is affected by gravity. On the other hand, since the general theory of relativity provides an exact description of the space-time around black holes, only a quantitative confirmation of the metric of space-time around black hole can be considered as establishing the theory. It is well known that the Kerr solution with 2 parameters provides the unique solution for stationary black holes that occur in nature. In my entire scientific life, the most shattering experience has been the realization that an exact solution of Einstein's equations, the Kerr metric, provides the absolutely exact representation of untold numbers of massive black holes that populate the universe. But a confirmation of the metric of Kerr spacetime cannot even be contemplated in the foreseeable future. That was said about 35 years ago. We have come a long way, but we are not there yet. We will be there, presumably in the next few decades, when X-ray interferometry comes of age, and you really map the polarization of radiation from the innermost region of the accretion disk. And of course, we are getting there as far as black holes or mergers are concerned. Finally, a few words about how such supermassive black holes may form. Supermassive black holes are most likely formed through a series of mergers of black holes that results in the centers of galaxies, such as our own galaxies. When galaxies collide, if you look at the Hubble deep image, beyond a redshift of 2 or 3, galaxy collision is extremely commonplace. And when galaxies collide, what you would expect is that the black holes at the centers of the galaxies will spiral in and eventually emit very low frequency gravitational waves. We haven't seen them yet. That's why space-based measurements are important. But anyway, this is one possible way black holes could have grown in mass. So the possibility is stars formed first, and then stellar evolution led to black holes. Various kinds of mergers, like Martin Rees suggested in a flow chart 30 years ago, could lead to these black holes grow from stellar mass to billions of solar mass, and then galaxy mergers will finally make galaxies become billions of solar mass. But there is a serious problem, an extremely embarrassing one at that. The problem is, the first quasar that was discovered at a redshift of less than 1. And that was shattering experience to see something with such a large redshift. But today, quasars have been discovered with a redshift of more than 8. The Lyman alpha line of hydrogen comes in the infrared. What is the problem with that? That means that massive black holes at the centers of these quasars were blazing away at a redshift of 8 when the age of the universe was less than 1 billion years old. So when the age of the universe is less than 1 billion years old, let us say a gravitational potential well forms in the dark matter for some unknown reason. Even the free fall time scale of matter to galactic size will be greater than the age of the universe at that time. So galaxies as we see them today could not have formed at a redshift of 7, 8. And yet the black holes are blazing away. So that rules out mergers, at least as far as these high redshift black holes are concerned. Perhaps even black holes at the center of M87. So one possibility that remains, the only possibility that has been entertained, is that a supermassive star forms. So the idea is somehow the gas in the potential well does not fragment into stars, but forms one gigantic star of 10 to the power 9 solar mass, or 10 to the power 10, or 10 to the power 11 solar mass. And how is this supermassive star stable? It is supported against gravity by radiation pressure, 1/3 AT to the power 4. Now, as the supermassive star contracts, shedding angular momentum, at some stage it can become unstable and collapse and form a supermassive black hole. What is the criterion for stability of such a star? We have discussed this 2 lectures ago. Namely, in Newtonian theory, the condition that matter will be stable is that gamma, the ratio of specific heats, Cp over Cv, should be greater than 4/3. If gamma is less than 4/3, compressibility of matter becomes negative and the star will spontaneously and dynamically collapse. Now, you'll say, well, the gamma depends on the pressure where you are in the radial distance. So we said you take a pressure average value of gamma. Well, people have calculated gamma using equations of state. It took 30, 40 years to do that. And there is a plot of the derived value of the ratio of specific heat as a function of density. And here is the Newtonian value of gamma 3, which separates stable regions of matter from unstable regions of matter. Now, in the early part of 1960s, Chandrasekhar turned to a study, a comprehensive Chandrasekharian study of the stability of stars in general relativity in an exact manner. This is a problem that von Neumann had suggested to him in the 1930s when the big argument between Eddington and Chandrasekhar broke out. And von Neumann had told Chandrasekhar the best way to settle Eddington is do this problem exactly in general relativity and convince him the collapse has nothing to do with relativistic degeneracy and questions like that. Then the war came, people became busy with things, von Neumann became busy with the war, atom bomb project and so on. And Chandrasekhar returned to this in his comprehensive fashion. In a series of papers, he discussed this problem in a mathematically exact manner. In the first or the second paper, he also discusses the post-Newtonian limit of this stability criterion. He shows in that paper that in the post-Newtonian limit, the critical value of gamma in general relativity is not 4/3, but 4/3 plus kappa multiplied by the Schwarzschild radius divided by the radius of the star. So as the star's radius becomes smaller and smaller, the deviation from 4/3 becomes significant. So there is the Newtonian limit, 4/3. In general relativity, the critical stability limit is a value greater than 4/3, and therefore this region, which was stable in Newtonian gravity, now becomes unstable. And of course, this particular plot is for behavior at high density, such as obtains for a white dwarf approaching the limiting mass. Please remember that for a white dwarf approaching the Chandrasekhar mass, gamma becomes 4/3, which is why the white dwarf collapses. But here we are not talking of densities of the order of 10 to the power 10, we are talking of very low density regimes. So a supermassive star is supported by radiation pressure, and what is the value of gamma for radiation? 4/3. So a star supported by radiation pressure is basically unstable, and then general relativity is making it more unstable, and therefore it is susceptible to collapse. So in that paper by Chandrasekhar, soon after quasars were discovered, there is a footnote suggesting that maybe quasars are powered by supermassive black holes, which are the result of a general relativistic collapse of supermassive stars. This is said in a very prescient manner in his footnote. So please remember, for a white dwarf, this general relativistic instability occurs when the radius of the white dwarf is thousands of times larger than the Schwarzschild radius. So the general relativistic instability preempts the Newtonian instability. So, although there are many, many difficulties with this scenario, this suggestion made by Chandrasekhar in '64 appears to me to be the only viable route for forming supermassive black holes, at least for the high redshift quasar black holes. So it's time to end now, and I would like to end it by quoting the great master himself. I shall read it for you. Black holes are macroscopic objects with masses varying from a few solar masses to millions of solar masses. To the extent they may be considered as stationary and isolated, to that extent they are, every single one of them, described by the Kerr solution. This is the only instance we have of an exact description of a macroscopic object. Macroscopic objects, as we see all around us, are governed by a variety of forces derived from a variety of approximations to a variety of physical theories. In contrast, the only elements in the construction of black holes are our basic concepts of space and time. They are, thus, almost by definition, the most perfect macroscopic objects there are in the universe. And since the general theory of relativity provides a single, unique, two-parameter family of solutions for the descriptions, they are the simplest objects as well. So I think that's a very good note to end on. And the next lecture, we will be shifting gears and talking about cosmology. I shall be quite happy to answer questions as usual. I'm sorry I exceeded the time, but I had warned that I would. Thank you very much. Yeah, feel free. Although there is a chairman for the colloquium, I think he has permitted me to ask you directly. Yeah. So that's what I said, yes. So could you just pass this microphone to the back? Yeah, please. Yes.
How does the precision affects the jets? How does the precision affects the jets?
What?
Does it affect the jets? The precision.
I'm saying there is no evidence of precession. Because if there is, in one or two galaxies, people have suggested that there are some complicated structures in the radio lobes, which people try to attempt by saying there is a precessing jet. See, if the jet precesses, even by a small angle, at 3 million light years, you can imagine the circle it would make in the sky. So how do you explain one hotspot? So the theoretical challenge is why the black hole doesn't precess. So somehow there is a locking of the angular momentum vector of the black hole with the angular momentum vector of the accretion disk. This problem was studied a long time ago by James Bardeen and his collaborators of how such a locking may occur.
And that toroidal thing that we have around the black hole, is it the accretion disk?
No, well, see, by the time you come to the innermost region, you no longer call it a disk because it doesn't look like a disk. First, it becomes very puffed up to a size which is thousands of times the size of the black hole itself. So it's a funnel. It's like a factory chimney. Right there in the center, there is a black hole. And then you're talking of matter that is going around there. So it is a material of the accretion disk which has managed to come in due to friction. I wouldn't call it a disk at that stage. That's why the word torus is used, or like a donut. People have used the Martin Rees has used the word Polish donut. It looks like a donut with a hole in the middle. Okay.
Yet it is so near the black hole, and still you said that it can have different spin axis than the black hole.
Yeah, it can.
I mean, it is very near.
See, it's a question of which has a larger angular momentum, right? So don't forget that you could have the magnitude of the angular momentum associated with accreting matter could be larger than that of the spinning top at the center. Right? So it need not be aligned, it may be aligned, but here they are suggesting it is aligned. Yes, there's one there and one there question.
Is it theoretically possible to view the other side of the jet which we can't see of one-sided jet?
What do you mean theoretically view?
Is it lower frequencies? Is it theoretically possible to view them like at much lower frequencies? So if there's a one-sided jet, we can never...
I don't understand where frequency comes in.
So because it's boomed in one way, we are able to see the frequency that...
You mean that way? Yeah, well, no, you work it out, how much the frequency changes by putting in the
there's a
Doppler.
cutoff which we cannot experimentally read.
Yeah, but you see, the frequency doesn't change as dq. It's only the surface, specific intensity that changes as dq. So frequency only changes by d, factor d. So something instead of being at gigahertz may come at meter wavelengths or something like that, but you can't think of something. But people usually observe these jets at a very wide range of frequencies anyway. See, they've been seen all the way from gamma rays to meter wavelengths.
Still they couldn't view it.
Yeah, there's nothing up to meter wavelengths. If you go to even lower frequencies, then radio telescopes don't have that kind of angular resolution. Only degrees, angular resolution will be in degrees, which you cannot see. So the highest angular resolution you can achieve at meter wavelength is something like with GMRT. Okay, and there you don't see anything on the other side. Yes. And the dynamical range of these modern interferometric observations is very high. So they can see intensity ratios of 10 to the power 4 and so on very easily. The dynamical range in a given observation. You can see brightnesses varying by 10 to the 4, 10 to the 5 and so on. So I don't think there is anything there at all. Yes?
Sir, we have said that...
Can you hold it closer?
Okay. Sir, we have said that the source of black holes, supermassive black holes, are the supermassive stars. So, but what leads to the formation of supermassive stars?
Well, how did galaxies form? Galaxies, there was gas in the early universe, there was this gas. If you look at the microwave background radiation, you see very diffuse distribution. So the standard picture is that some sort of a gravitational potential well forms in the dark matter, and then matter falls into this. And at some stage, and then rotation becomes important, and you say, this is a galaxy consisting only of gas. And then the gas fragments to form stars. And the stars evolve and become neutron stars or black holes, and that's the old story. The statement here is at a redshift of 6, 7, 8, the free fall time in Newton's gravity, just for matter to fall from infinity to something of the size of 100,000 light years, which is the size of a galaxy, that free fall time is larger than the age of the universe. So what one is saying is somehow a dense, stable object which is rotationally supported, which we later on will call a galaxy, hasn't formed. This is a star. This is a gas cloud. The difference between a gas cloud is not gravitationally bound. This is gravitationally bound and stable against gravity because of radiation pressure. And that object is what you call as a supermassive star. Okay. Whether the supermassive star is hot enough to synthesize elements and so on, nobody is saying at this stage. What is interesting is that some objects, not of billions of solar mass, but maybe hundreds of solar mass or thousands of solar mass, such stars also formed. How do we know that? Because the way you see the quasars is by seeing the spectrum of atoms along the way. So even when you look at a high redshift quasars, you are seeing absorption and emission lines of elements, which we know can only be produced in stars. So the original conjecture, again by Martin Rees, was that somehow before what we call as stars formed, which was after what we call as galaxies formed, there was a first generation of stars that somehow formed. Why they formed, how they formed is a different story. And you need to invoke that to explain the observed spectrum of quasar light. But that's not what I mean by supermassive stars. The supermassive star is just this gas which is falling into the potential well. And if that becomes unstable and collapses, it can become a black hole. Yes?
So, why was the radio flux from the quasars found to be varying?
Speak louder.
Why was the radio flux from the quasars found to be varying?
Why was it found to be variable?
Varying. I mean,
It was found to be variable.
is there an explanation for why it was?
Yeah, the explanation is you see, remember what is the see, imagine search for extraterrestrial intelligence. We do the following experiments. We cover the whole surface of the earth with radio antennas. And we say, when I give the signal, you all emit a pulse of 21 centimeter radiation. Okay, fine. So I give the signal at a time t equal to 0. Then I ask, who are the people who would have radiated after time delta t? It will only be antennas within a radius which is less than c delta t, because only those antennas received my signal saying emit. Therefore, the moment I have a time signature of radiation of the order of delta t, that immediately tells me that that radiation can only have emanated from a region whose size is smaller than c delta t. So what this means is, we don't know what is there at the center of this quasar. We are saying that there is something in the center of that center whose size cannot be more than this, because that's what is emitting the radiation. Okay, now it is emitting more, now it is emitting less. So there is a conspiracy, and that conspiracy can only be formulated within a distance c delta t. And that was the argument that Jocelyn Bell used to say it must be a neutron star or a white dwarf.
So also I had another question. What is the process of radiation in the lobes? Is it also synchrotron?
It's synchrotron radiation. Because the signature of synchrotron radiation is that the intensity as a function of frequency is nu to the power minus something 0.5 or to 0.75 or something like that. Okay, so that's the signature of synchrotron radiation. And it is polarized. Good. If there's, yeah, thank you.